Okay, so let's start now with the circuit diagram problem. Consider the circuit diagram below of 5 known resistors and 2 batteries. So all resistors are known and they're quoted in units of R. So 5 are here, 3 are here, 2 are, 4 are. There's one loop here with one battery. There's one loop here with another battery, epsilon here. So let me redraw this circuit diagram, and I'm on purpose leaving the circuit diagram like this. So you have here, first of all, the battery here, the first loop here. Then you have here a resistor 5R. Here's a resistor with value 3R. Then you have here a junction here. Let's label this A and this B here. And within that junction there's another resistor here. And then we have here the second loop. And down here a battery. Another one here. And then last but not least also here a resistor. Okay. So that's the complete circuit diagram. So let's label all components. So this is 2 epsilon plus minus. This is R here. This here is epsilon. This is 4R, 2R, 3R, and 5R. I've labeled the the junctions, and so now next step is to draw a current direction, and you're completely free to choose any direction you want. So I chose here the current going down. Here's the battery plus going around here, so that's the current in here. Now you have a junction here, so I'm drawing here a current now up, I2 here, and then I'm having here a current I3 here, plus is here, minus is here, so current I3 going like this here, I3. So that's the current here in this part here. And last but not least, now the loops. So you choose one point here, and remember this loop. The looper is entirely, at the end of the day, a consequence of the conservation of the conservative nature of the the Coulomb force, and therefore the electrical field. You're going around in loop once. So I call this loop 1 here. I call around this loop 2 here. And then we have a third loop going around all around once here. So this would be loop 3 here. So this graphical preparation is absolutely essential in applying Kirchhoff's rules. So what do we know? We know the battery values, but we do not know the current values, I1 and I2 and I3. So first of all, let's apply now step by step. In part B now, the junction rule here. So A and B. So the way I'm always doing this is junction A, current flows out. Consider it just like water flow. Current flows out of junction A, and water flows into junction A from I2, and current from water flows from current I3 into the junction. So you're losing something here from current I1, but you gain something for current I2 and I3. So therefore we have minus I1 plus I2 plus I3 equals to 0. In the case of junction B here, you're gaining something relative to current 1. Current I1 flows into junction B, but current I2 flows out of that. That's why we have a minus sign, and also current I3 flows out of junction B. That's why we have minus I3. So therefore we have I1 equals to therefore I2 plus I3. And you can see here these two equations are mathematically not independent. we have now how many unknowns in this problem? We have three unknowns, namely the currents and the current I1, I2, and I3. But we know the resistor values and we know all of the batteries. So now let's come to the second part now, formulating all loops here. And what I told you in class, think of this essential step here as your free body diagram, together with a coordinate system translating this, applying second Newton law. If you do not get this here right, your work concerning now the second loop will not be correct. So let's do this really carefully here. 1, 2, and 3. So let's start with 1 here. So you're going into, so let's start, you can choose any point you want. Let's start with this point here. You're walking now in this direction here, clockwise direction, through resistor 5R in the opposite of the current direction. That's why we would have here plus the voltage drop. So this would be I1 plus I1 times 5R. We're walking now through the battery from plus to minus, so this would be negative from a higher to a lower potential, minus to epsilon. And then we're crossing the resistor 2R in the opposite direction, so we have here plus I2 2R. And then we have here the same thing in the opposite direction for current I3 relative to resistor 3R. We have then plus I1 3R equals to 0. Now let's go to a second loop here. So let's start also here with this point here in the bottom. We walk now through resistor 2R in the same direction as the current. So then we have here minus I2 2R in the opposite direction for here. So this would be, hold on one second here, plus I3R. Then we have here the battery from plus to minus, minus epsilon, and then plus I3 4R. 4R equals to 0. And last but not least, going around all around once, let's start here. So then we have here plus I1 5R for here, minus 2 epsilon for this battery. Then we come to this resistor here. This would be plus I3R. Then the battery here minus epsilon. Then the resistor here plus I3 4R. And last but not least, this resistor R here plus I1 3R equals to 0. All right. In the same spirit as I've identified that these two equations for the three unknowns are not independent, let's analyze these sets of three equations here a bit. So let's first simplify that. So for 1, we have now I1 here, so we can combine this and writing this in fact as I1 8R minus 2 epsilon plus I2 2R equals to 0. And you could have already done this in one step, namely you see these two resistors 5R and 3R in series. You could have combined them as 8R and would have then therefore only these two resistors, 2R with current I2 and resistor 8R with current I1. This is the same thing as here. So then second, we have here, we could combine now these two resistors before and 5R. Now this you see this also here in the equation. You have here a term I3R and I3-4R, so gives 5 I3R. So therefore we have now here minus I2 2R minus epsilon plus 5 I3R equals to 0. And the third part now is we have here I1 and I1 here, so this gives us now I1 8r. Then we have here I3r and I3-4r. This gives us plus 5 I3r. And then we have here minus 3 epsilon equals to 0. Minus 2 epsilon minus epsilon. So now let's analyze them a bit. Namely, let's add the first and second equation. So if we're adding the first and second equation, then what do we get here? We have here I2r minus I2r cancels out, and then you have here I1-8r left, plus 5 I3r minus 3 epsilon 0. So we're basically getting the same thing out of adding equation 1 and 2. So now what I want to do here now is solve these sets of three equations for these sets of equations for the three unknowns, namely the currents. So this is now the last part in part D here. So how do we do that? So let's first begin here by realizing that I1 can be replaced by I2 plus I3. Then I have an equation involving I2 and an I3, and I have here the second equation is an equation involving I2 and I3. And then I have two equations with two unknowns, and I solve that. And then we take another one and solve them for I1. All right, so this is a little bit of algebraic work, so be careful with that and write things down really neatly and not to make any mistakes here. So let me rewrite this a little bit. Let's start with equation 1 here. So I have here minus 2 epsilon from here plus I2 2r from here, and then I have here plus 8r times, and now I1 are replaced by I2 plus I3. So this I2 plus I3 equals to 0. So now I can rewrite this as minus 2 epsilon plus I2 2r plus 8r I2 plus 8r I3 equals to 0. So now I can simplify this a little bit further, combining the I2 terms, and then I get in here finally minus 2 epsilon plus 10 I2r plus 8 I3r equals to 0. And now you see here we have the two unknowns here, I2 and an I3. And let's go back now to the second equation. We have I2 and I3. And let's compare this a little bit here. If I were to multiply equation now 2 with 5, then you have here minus 10 I2r, and here I have 10 I2r, and you add these two equations, and then we can solve it. So let me rewrite this first equation here now. So first equation rewritten now a little bit would be minus 2 epsilon plus 10 I2r plus 8 I3r equals to 0. Now let me multiply now the second equation by 5 here. So let's multiply this here by 5. So what do we get then? Then we get minus 10 I2r, so this would be minus 10 I2r, minus 5 epsilon, minus 5 epsilon, and then here 5 I3r times 5 is plus 25 I3r equals to 0. So now we can add this, and the term involving I2 cancels out here. So then what do we have left? What we have left then is 5 plus 25 is 33 I3r minus 2 epsilon minus 5 is minus 7 epsilon equals to 0. And then you can solve this now for I3, and you're getting 7 over 33 times epsilon over r. Okay, Alright, so that's this. So now we have already I3. So now let's solve the next one then for I2. And for I2, you can now take the equation. So the second equation here we just solved. We have now I3. So here is I2, and I solve this now for 2. So I take this term here to the other side and divide by 2r. So I2 equals to 2r equals to, and then you have here 5I3r minus epsilon. So let me write this down. So you have then 1 over 2r, parentheses, 5I3r minus epsilon equals to 1 over 2r, and then we have here 5r times 7 over 33 epsilon over r minus epsilon, so r against this, and then 5 times 7 is 35. So then we have here 1 over 2r, and then we have here 35 over 33, epsilon minus epsilon, common denominator is 33, so then you have 35 minus 33 is 2, so 2 over 33 epsilon, and this 2 goes against this 2, so therefore you have then 1 over 33 epsilon over r. So let me rewrite this. I2 is therefore 1 over 33 epsilon over r. I'll label this as page 1, page 2 here. So and now we do the last part, namely I1. And I1 you can simply get as I2 plus I3. You sum all of both of those, and then you're getting here 7 over 33. 1 is therefore 8 over 33 epsilon over r. So if you come to this point, I strongly encourage you to check your result, that this is really indeed the case. So let's go back now to our set of equations here. We just used equations 1 and 2. So let's now take our result for I1, which we just obtained, and the initial result for I3, and plug it in the third equation. We should indeed get this get the correct result. So check with 3. So what do we have then? So we have then I1, maybe write this quickly, I1 8r plus 5I3 r minus 3 minus 3 epsilon. So what do we get then? I1 is 8 over 33 epsilon times 8. I already cancel out the r and r, plus 5 times, and now I3 is 7 over 33, 7 over 33, epsilon over r, so the r goes out, minus epsilon minus 3 epsilon. So what is this? So 8 times 8 is 64. You have 64 plus 35 minus, the common denominator is 99. And indeed, 35 plus 64 is 99. So this is over 33 epsilon, and this is indeed 0. Good. All right, so that concludes this problem.